towards that goal are diamond and silicon carbide quantum photonics. And I will be talking more about it later on today, but we actually, as you'll see in a moment, combine a variety of impurities in semiconductors with photonics in diamond and silicon carbide, and we're currently able to achieve very high quality of these structures, and we're moving towards scaling. So as qubits, we actually use optically interfaced semiconductor spin qubits. For those of you who may actually not be familiar with this particular platform, this is, in terms of the physics, exactly the same as superconducting qubits in microwave cavity that are shown on the left. For us, a qubit is basically a spin of an electron of an impurity inside of a semiconductor optical cavity. For example, we use color centers in diamond and silicon carbide as quantum emitters, artificial atoms, and then build resonators around them. And physics, again, is exactly the same as for superconducting qubits, but on the other hand, our platform is smaller by a factor of greater than 1,000. So we use a variety of sophisticated fabrication techniques in order to implement these systems. It's not really traditional microfabrication as in case of superconducting qubits, because everything is much smaller, so you need to use more sophisticated fabrication. And we also use, of course, semiconductors on a brighter node, not superconductors, so it's kind of more accessible and easier to process. We also have a possibility of operation at higher temperatures. We don't really need to use dilution refrigerators. We still have to cool down the chip, but temperatures of few Kelvin are working just fine, which means that you can actually do experiments in simpler closed cycle cryostats instead of dilution refrigerators. We already have excellent optical interfaces for these structures, as opposed to superconducting qubits, where you basically have microwave interfaces, and in order to network them, you have to build quantum transducers that people are still developing. But we have excellent optical interface for granted. And maybe most interestingly, for scaling of these platforms, the number of 2-qubit gate operations that you can perform per electron spin coherence time is actually greater in these systems than for superconducting qubits. And that means that eventually you can build larger depths of quantum circuits. These systems operate at very high speeds and high frequencies, so within the coherence time, you can actually perform many millions of operations. So as qubits themselves, we use impurities in semiconductors, actually spins of impurities in semiconductors. In diamond, we're particularly focused on inversion symmetric color centers. That's shown here in this table, which actually summarizes some of the main properties of these color centers. There has been a lot of activity over the past several years on silicon vacancy color centers in diamond. And all of these centers are basically produced by removing 2 carbon atoms in diamond and actually inserting 1 extra impurity, interstitial impurity, in between these 2 vacancies. So most of the effort has been on silicon vacancies over the past several years. You may have seen a lot of exciting work in that space. We've also done a lot of work on silicon vacancies, but at the moment, we're primarily interested in thin vacancy color centers. All of them are inversion symmetric, and that means that they're, to the first order, immune to electric field, and they don't actually exhibit DC start shift. Again, to the first order, which means that they're more immune to the environment, and you can embed them inside of the structure and so on. But the reason why we're more interested in thin vacancies than silicon vacancies is because they have much larger ground state splitting from 50 gigahertz to 850 gigahertz, which means that they don't suffer from decoherence, phonon decoherence processes that require silicon vacancies to operate at millikelvin temperatures for the best results. As opposed to silicon vacancies, you can do experiments again in closed cycle cryostats at several Kelvin of temperature, and also thin vacancies have significantly higher internal quantum efficiencies than silicon vacancies. So what is the state of the art for these color centers? For silicon vacancies, I'll just very briefly summarize that people have demonstrated excellent photonic interfaces for silicon vacancy inside of a diamond resonator. People have also demonstrated 2-qubit interaction for 2 silicon vacancies inside of the same cavity that are tuned with magnetic field. That was the work at Harvard. So people are pretty much at the level of scaling corresponding to 2 qubits. And also for thin vacancies, research started to ramp up about a year ago. We have demonstrated excellent properties of these thin vacancies inside of the diamond structures, and similar work was published in collaboration between MIT and Cambridge, groups of Dirk England and Mette Atature. They exhibit narrow line widths. They're not really affected by surfaces, and I'll actually show you in a moment that we are also able to couple them into optical devices right now. So we're able to put them inside of the optical structures, optical waveguides in this case, which are outcoupled with grating couplers without degradation of line width. The line width of the thin vacancy color center is about 36 megahertz after embedding inside of the structure. So we are working further on performing scaling of these systems, but we're working with optically interfaced spin qubits. As I mentioned at the very early slide, you have to deal with a variety of non-traditional fabrication methods because everything is much smaller than for superconducting systems, because you are operating at optical frequencies and everything pretty much scales down with the wavelength. And you also have to controllably insert these quantum emitters inside of the semiconductor lattice. So what we're doing is we're developing a variety of techniques that enable us to insert them at precise positions inside of the diamond, in this case, in a regular grid and with high yield. And what people normally do to insert these color centers in diamond is either ion implantation or using focused ion beam, which is again ion implantation, but in a controllable way. But all of these processes have to be performed at high energies, hundreds of kilo electron volts. And that process actually damages the structure of crystalline structure of diamond, introduces some local strain, and then lifts the inversion symmetry of the color center, which leads to its sensitivity to the environment, including first order to DC start shift. So what we want you to do is avoid this, avoid all of these processes that are leading to degradation of the crystalline structure of the material, but at the same time insert color centers in a regular grid. And in collaboration with Nick Milosh and Ziek Shen at Stanford, we have developed this process of shallow ion implantation and subsequent diamond overgrowth. In this process, we basically start from high purity diamond. We mask it using traditional electron beam lithography, then perform low energy ion implantation. That's why we call it shallow ion implantation. We do that at 1 kilo electron volt as opposed to hundreds of kilo electron volts that are typically used for the process. And of course, that leads to minimize the damage of the lattice, but of course leads to color centers that are very close to the surface of diamond. And that's not really desirable for experiments. So what we have to do is regrow a high purity layer of diamond on top of the structure at the very end of the process. And here you see resulting structures. It's a regular lattice. And also from measurements themselves, we actually see that spectra are much cleaner. We eliminate some spurious peaks in the spectra corresponding to a variety of other defects. And also line widths of the color centers themselves are much narrower. And another really desirable aspect of this, in addition to the quality of the color centers, is that you can use very simple masks in order to perform these mask implantations, which is not really the case for high energy implantation, because these regular resist masks, for example, would not really resist implantation at energies of 100 kilo electron volts. So we have this process of introducing color centers in diamond in a controllable way and with high quality. And I'll tell you a little bit later how we actually embed them in optical structures. Before I discuss that, I also like to mention that about half of my work focuses on silicon carbide, and in particular on silicon vacancies in 4H polytype of silicon carbide. This is another emerging semiconductor platform, a wide bandgap semiconductor, which hosts a variety of exciting color centers. And our team, in collaboration with Jörg Rastrup in Stuttgart, and on the theory side with Sofia Economou at Virginia Tech, we're looking into silicon vacancy in 4H silicon carbide, which is basically just absence of a single silicon atom in 4H silicon carbide lattice. And from this particular system, people have demonstrated very exciting results in distinguishable photons generated from the system, 65 megahertz transition line width, lifetime limit is 35 megahertz, and also electron spin coherence time of 20 milliseconds. And this coherence time may not sound very long in the context of, for example, atomic physics systems, but keep in mind that at these optical frequencies, and in particular, when interfaced with optical devices, we can actually perform operations at tens of gigahertz speed. So this is a pretty long coherence time. So transitions are very narrow. There are basically two, depending on the positions of the silicon atom that is missing in the lattice, two zero phonon lines, which we refer to as V1 and V2. They're both in the range around 900 nanometers, so a little bit more accessible, easier accessible than diamond color centers, which are typically around 600 to 700 nanometers. This is a more traditional quantum optics range where we've done a lot of experiments with indium arsenide, gallium arsenide quantum dots. And transitions are also very stable. I mean, here on top right, you see measurements of these transitions over 5 hours, but we've done even longer measurements, and they exhibit very excellent stability. So this is the set of kind of qubits that we're interested in, right? And this all looks great, right? You have long-lived qubits, you have excellent electron spin coherence times, you can embed them in structures, as we'll be discussing in a moment. So why have not we and others scaled this to the scales of other quantum computing, quantum information platforms, such as atomic physics or superconducting qubits? Well, the problem is in inhomogeneities. And that is actually visible in these pictures that I showed you before. After implantation into the structure, it's extremely difficult to achieve perfect yield of implantation and obtain them all at the desired positions, although we're actually doing pretty well right now with the new methods. But we will never really have a perfect yield of these color centers at the desired positions. And that's fine. That's also the case with other platforms. In atomic physics, people also have to work with optical tweezers to kind of reconfigure atomic systems and fill up the empty spots, or in superconducting systems, they also need some level of reconfigurability. But the other problem that we have to face and deal with is what you see on the right, and that's inhomogeneous broadening. Normally, I mean, if you have a single emitter, you would see the spectrum. This is in this case for silicon vacancy, as shown with the red curve. But you know, when you look at the ensemble of these color centers on the same chip, you will actually have transitions that vary by about 30 gigahertz. And this inhomogeneous broadening, so line width is pretty much preserved, but transitions vary from color center to color center, are results of imperfections in the environment and the crystalline structure. I said that these are inversion symmetric color centers that are immune to the environment, but any strain in the sample would actually leave that, and it would not be immune to the environment anymore. So this is primarily a result of strain in the sample and then some other resulting impurities. So we have about 30 gigahertz of spectral broadening for silicon vacancies. Again, this depends on the color center and the materials that we're using and the purity of the materials, but there is about 30 gigahertz of broadening that you have to deal with. So in order to deal with that and to address that, we've developed a variety of methods for tuning. And for diamond, we have developed cavity-enhanced Raman scattering. where basically we have shown that we can compensate for much more than inhomogeneous broadening of the color center by off-resonant Raman driving. And the idea is very simple. It's something that people use all the time in atomic physics. You have a silicon vacancy, you just drive it with the off-resonant laser, and you can change the tuning from the excited state. And in that process, by changing that detuning, you will also change the frequency of the Raman scattered photon. And we have shown that for silicon vacancies inside of the optical structures, we can use this mechanism to change the frequency of the scattered photon by up to 100 gigahertz. And remember that we have inhomogeneous broadening of 30 gigahertz, which means that we can compensate much, much more, a factor of 3 or more than the whole inhomogeneous broadening in the system, which means that you can interface different color centers. But of course, in this particular approach, you would have to drive them with different lasers. And for smaller sizes of quantum systems, that's okay. But of course, when you go to much larger sizes of quantum systems and many elements, having a separate laser to drive each qubit is probably not going to be the best approach, which is why we are developing some other approaches that I will show you in a moment. So the other method that we've worked with, and in particular for silicon carbide, is DC start shift. For silicon carbide color centers, silicon vacancies, we can actually quite efficiently use the DC start shift, put electrodes for each color center, and we can tune transition by about several hundred gigahertz. Here you see tuning. This is start tuning for silicon vacancy transitions by 200 gigahertz. And that's more than enough for compensating all of the inhomogeneous broadening. But of course, the configuration here would assume that, again, you need a separate set of electrodes to tune each color center on the chip. I should mention that in this process, we have pretty stable emitters. Even after we apply DC start shift, we still have very stable transitions, and we can, even on the tuned emitters, do pretty much the same experiments as on the ones that are not tuned. But going back to the idea of tuning with this approach, you will have to put separate set of electrodes and wires on the chip that would tune each color center separately, which technologically is easier than driving each one of them with a separate laser, but still we've been wondering whether we could do something more scalable than this. And this brings me to Floquet engineering, which we've been playing with recently. Of course, the idea of Floquet engineering and periodic driving is not new. People use it in superconducting and atomic physics systems, and also for color center ensembles. But we were interested whether we could use the ideas of Floquet engineering to kind of optimize the driving, and not just to go beyond the periodic driving of the system, which produces Floquet eigenstates at the output, and instead design the drive, this optimal kind of periodic drive by superimposing different microwave harmonics, and use that to engineer the spectrum of the emitter in the convenient way, so that if you have some inhomogeneously broadened spectrum and you apply these optimized microwave drives to different emitters in the system, you can actually interface them to each other more efficiently. And experimental results that I'll discuss in a moment are shown on the left, and the idea of interfacing emitters with optimized driving is shown on the bottom left. But I'll now actually show you some of our very recently published results on spectrally reconfigurable quantum emitters by Floquet engineering. So if you're familiar with the idea of Floquet driving, when you apply periodic driving on an atomic system, the set of eigenstates is Floquet eigenstates, and that is visible in both theoretical analysis for our color center and also experimental analysis shown on the left. So what we're doing here is we're driving single silicon vacancy in silicon carbide with a microwave drive. So this is not a DC start shift. Instead, we're basically applying high-speed microwave driving which is faster than transition of the system. So we're actually applying few gigahertz of microwave drive. And experimentally, you observe these new Floquet eigenstates that emerge in the spectrum, which are also expected in theory. So it's not just these two stable transitions that I showed you before, but instead there is this kind of spectrum of Floquet eigenstates that emerges. And although you are driving the system with a high-speed microwave signal, you don't really sacrifice its quantum optical properties. If you perform second-order photon correlation measurements, you still see anti-bunching. You see some signatures of this periodic driving in the G2 signal, which is a second-order coherence function, but you still have anti-bunch signal, which indicates that you are performing all of these experiments with a single emitter. Of course, this is just a very simple periodic driving, Floquet driving, which some of you may have also seen in quantum optics or atomic physics classes. But as I mentioned at the motivation slide, we wanted to go beyond that and also engineer the signal, microwave signal that we are applying to the system. And theoretically, idea is described here on these slides. Basically, what we wanted to do is achieve particular spectrum at the output for our quantum emitter. And of course, spectrum depends on the in your Rabi frequency and intensity with which we are driving the system, but it also depends on the microwave frequencies that you are using to drive the system. But if you're not driving it with a single microwave frequency, if you're actually taking multiple microwave harmonics, your driving signal would look more complicated. It's not just a simple periodic signal, but also your output spectrum of your quantum emitter will start to change. And you can produce these beautiful spectra at the output, but you can also apply some more complicated microwave signal like the one that I show on the left, and then produce an asymmetric spectrum at the output. So this kind of led us to the idea that we could design a desired spectrum, like start from a desired spectrum that could be used to interface a variety of the emitters on the sample, and then optimize the microwave driving signal in such a way that we obtain that particular spectrum at the output. And we've done that experimentally for single silicon vacancy in silicon carbide. Here, for example, experimental results for a 2-color microwave drive. Experimentally, you see these 4 peaks in the spectrum instead of the 2 peaks. They correspond to the transitions for spin 3/2 and spin 1/2 manifolds of silicon vacancy. And this also matches what you expect to see in theory. If you go to a 4-color microwave drive, as shown on the left, spectrum becomes more complicated. There are 4 peaks in spin 3/2 manifolds, 4 peaks in spin 1/2 manifold, and again, everything matches the theory. So these are just demonstrations that you indeed can engineer the spectrum of the output at the output of the color center by designing the drive. And in this process, you are not really negatively affecting the properties of the qubit or quantum emitter. In fact, we've shown that we can do optical coherent control of such modulated quantum emitter, and basically the system performs exactly the same way as without the microwave modulation. We can put the system into arbitrary superposition of the anywhere on the surface of the Bloch sphere by optical driving, right? So we're interested in primarily optically driving the system with pulses, but at the same time, we're interested in using microwave modulation in order to engineer the spectrum of the emitter. And beyond this control and spectral reconfigurability of the quantum emitter, this approach can also be used to shape single photon emission by this pulse modulation, because you can drive your emitter with microwave pulses and simultaneously excite it with optical pulses. And we have shown that by controlling the phase between the two and the excitation power for microwave and optical field, we can in principle build very high quality single photon sources that are completely anti-bunched, but also we can control and increase the indistinguishability of the single photon source, and also increase the efficiency of the emission into a particular channel. So in principle, you can build deterministic single photon sources with this approach. So now the other ingredient of building all of the quantum systems, apart from qubits, of course, are connections between them. And working with optically interfaced qubits, we're interested in optical interconnections. Of course, for microwave interface qubits, those would be microwave connections, but we have to implement efficient optical interconnections for our spin qubits. And of course, optical interconnections are also preferable for a variety of approaches, because eventually you need optical connections in order to connect your systems into some functional quantum networks. And this brings me to the idea that my group has been looking into for a really long time, about 15 years or so now, which is designing photonics in a better way. And this is not really only applicable in the context of quantum systems, but we're also interested in this in the context of classical photonic systems. For example, here you see some of our 2-channel and 3-channel wavelength splitters that we've designed in silicon that are very compact and also very efficient. And when we measure, I mean, they're very non-intuitive. Of course, they look very different from wavelength splitters that people have normally used in photonics. But in this case, we can actually design them in such a way that they're robust to environmental and fabrication errors. And when you measure transmission for many, many devices on the chip without any post-tuning, they all perform the same for all of these. And we've developed software suite that we call SPINS, Stanford Photonics Iverse design software, that quite a few companies and research groups are using. We also have open source basic version SPINS-B on GitHub if you are interested in playing with this. And the idea of this software is really in combining classical optimization techniques with high-speed electromagnetic solvers, and using this to design, kind of search through the whole parameter space of fabricable structures in order to implement particular function in a robust or a way or efficient way, or implement new functionalities. So the process is pretty efficient. For example, for 3-dimensional device of this footprint here, we're designing mode converter, which has a footprint of about 2 by 1 micron. The process is shown here. This is the first stage of optimization, and you see electromagnetic field on the right. And then we have the second stage of optimization, where basically we build something that is fabricable, binary optimization. And again, I'm showing the cross section of the structure, but this is fully 3-dimensional structure, and you see really mode converter at the end of the process, and you incorporate fabrication constraints in the process and so on. So this full optimization, which takes about 400 iteration in 3 dimensions, takes about 1 hour on gaming GPUs. And we believe that this could be sped up even further by maybe a factor of 10. But again, you don't need any special hardware. These are just gaming GPUs. And we spent a lot of time trying to really develop also high-speed solvers that would work on this accessible platform. So you can design, structures in a matter of like an hour or a few hours, depending on the size. And we've designed many interesting devices and circuits using this approach. I already mentioned wavelength demultiplexers. We also use this to design a layout for dielectric particle accelerator, a laser-driven particle accelerator. So this is a block of silicon that is engineered so that you can accelerate incoming electrons, kind of to build compact on-chip accelerators. This is non-reciprocal pulse router in silicon. All of these here are in silicon. And the process is also compatible with foundry fabrication. This work on the right is also from a foundry, as I mentioned to you in a moment. And although everything that I showed you so far has been done in silicon, the process of the design is completely agnostic relative to the material. And of course, we've applied it to diamond and silicon carbide, but you can apply it to a variety of other materials. You just need to know material properties and fabrication constraints. So for those of you who are interested in foundry-based fabrication, which of course is very important for building any very complex photonic systems, this is fully compatible with foundry fabrications, and we've collaborated with several foundries, but initially with AIM Photonics and the group of John Bowers at UC Santa Barbara. And we have shown that the same devices that we made in our fabrication facility at Stanford using electron beam lithography could be made in AIM Photonics on silicon chip. This is theoretically predicted behavior. And then for foundry fabricated devices, when we measure all of them on the chip, they basically perform exactly the same. So foundry fabrication is completely accessible. And of course, most foundries just work with silicon, but in principle, you can actually work with any other materials. So going back to quantum systems, which is the topic of my talk, we are relying quite heavily on this inverse design in the context of building diamond and silicon carbide circuits. And for quantum systems, it's even more critical to build efficient photonic structures because you're really working with single photons or some quantum states of light that are quite fragile, and you certainly cannot really afford to lose 40 to 50% of them at variety of couplers in your circuit, as people often do even in commercial classical photonic systems. I mean, couplers are generally, even in commercial systems, having efficiencies of around 40% or so. So to avoid losses, undesirable losses, and build kind of reduce experimental time and increase the scalability of the system, we started relying heavily on the inverse design approaches to build circuits in diamond and silicon carbide. And here you see some of the structures we implemented in diamond. And for any material that you are using, you can incorporate fabrication constraints for that particular material. Processing diamond is harder than processing silicon, but we can actually incorporate in the design process how well we can process diamond, what are the minimum feature sizes that we can do, and so on, and then build the structures. And here is one example how dramatically this impacts our experiments. In older experiments that I showed you earlier on, for example, the ones with Raman driving, we relied on these notches in order to couple light into the structure. They have very low efficiency, 1 to 2%. If you replace them with these optimized couplers, inverse design couplers, you can basically reduce experimental time by a factor of 500. After 1 second integration, you see much stronger signal at the output, as opposed to 10-second integration for these notches, where you start barely see some signal coming from the resonator. And signal to noise ratio is much better, and experimental time is reduced without any degradation on the cavity itself, which is very important for scaling systems further. We do the same in silicon carbide, but before I talk more about silicon carbide, I'd like to say a few words about silicon carbide actually as a material. Even apart from quantum optics or quantum photonics, and I already mentioned that silicon carbide hosts some high quality quantum emitters, silicon carbide is a very interesting material for photonics, and it may in fact be ideal photonics material because it's available on wafer scale, it's inexpensive, it's silicon compatible. You pretty much use the same process to make structures in silicon carbide and in silicon, same chemistry, same etching. It has excellent thermal conductivity, large band gap, but also it has a strong optical nonlinearity, both second and third order, and it's also piezoelectric. And there is no other material that actually covers all of this, that exhibits all of these properties at the same time. The only problem with silicon carbide when we actually started working on this was that we didn't really have an access to silicon carbide on insulator with high purity, which is what you need in order to make photonics. right? And if you are working on silicon photonics, you probably know that silicon on insulator wafers were commercialized about 20 years ago, and that was around 40 years after commercialization of silicon wafers. And after silicon on insulator became accessible, that's when silicon photonics really took off, because you need this thin film of material where you can guide light and build all the photonics. And same thing happened with lithium niobate about 10 years ago when thin film lithium niobate became accessible. That was again about 2 decades after bulk lithium niobate wafers were commercialized. And in the past 10 years, we've seen a lot of exciting results on thin film lithium niobate platform. On the other hand, silicon carbide was also commercialized in the 1990s. That's bulk silicon carbide. You can get it in 6-inch wafers, for example, from companies like Cree, but there was no commercial silicon carbide on insulator as of last year. And we had to come up with the process to produce it with very high quality in order to do all of these experiments. And I'd like to mention that, if you're interested in nonlinear optics, silicon carbide is material that is much easier to process than lithium niobate. And its second order nonlinearity is maybe a factor of about 3 lower than for lithium niobate, but you can very easily compensate for that difference in chi2 by making high quality photonics, as I'll show you in a moment. So I really think that silicon carbide is an ideal material, and on top of everything, it hosts really high quality qubits. So how do we make silicon carbide on insulator? We do a very simple thing. We start from silicon carbide, bond it on oxidized silicon, and then tin it. First do coarse tinning, then fine tinning, and then end up with chips of silicon carbide on insulator. And this process is actually also scalable to larger chips, but for us, a few millimeters of a chip size is sufficient to do a lot of experiments and build pretty much all of the circuits that we're interested in. Before we did this, we also tried smart cut, which relies on ion implantation, which is what people use to make silicon on insulator, but that really didn't lead to high quality material, because you bombard material with ions, and that leads to unintentional defects inside of the structure. So that's not good for quantum optics in particular. And also for classical photonics, it degrades the properties of the interfaces. So right now, we can make photonics with very high quality. We have very low loss, extremely low loss, smaller than in silicon on insulator. We have quality factors greater than 5 million in the infrared. These are some of the structures we made in silicon carbide, and you see also inverse design couplers. We apply the same approach here. We again measured quality factors, most recently around 5 million. This is a little bit older results where we have Q of about 1 million. This was measured via this inverse design grading coupler and transmission through evanescently coupled waveguide to a ring resonator. And all of the structures that you see here are basically coated, covered with oxide. So they're buried in oxide, like typical silicon on insulator structures. So they're not really suspended structures. I mentioned that silicon carbide has excellent second order nonlinearity. Last year, we first performed second harmonic generation experiments. In silicon carbide, we measured efficiency, and this is efficiency measured on the signals coupled to waveguide of 360% per watt. But at that time, we had Q factors for resonators that are very smaller by a factor of around 10 or more, a Q factor of 100,000 relative to millions that we have now. So we think that this number actually should be now much higher, probably by about 2 orders of magnitude. And we're working on repeating the measurements. Recently, we've also looked into optical parametric oscillation. We demonstrated that we can have OPO on silicon carbide with only 8 milliwatts of threshold. This is relying, in this case, on chi3 nonlinearity, but you can actually also build it with chi2 nonlinearity. And you can actually see even the signal of microcomb emerging in this case at higher powers. And even more recently, this has not been published yet, we've demonstrated chi3 soliton frequency comb in silicon carbide, again with small threshold powers. This appears at the pump powers of 2.7 milliwatts, and this power is measured in the waveguide that is coupled to resonator. So this is actual coupled power to the waveguide. And again, soliton frequency combs are important because that's the regime in which you have a stable frequency comb on chip. They have not really been demonstrated in many materials, but this is quite exciting and actually comparable, for example, to Tantala platform that the group of Scott Pappett NIST is using to make practical microcombs. So that's nonlinearity. In silicon carbide, again, going back to quantum optics, you can put everything together, these high quality photonics together with quantum emitters. We've demonstrated a large enhancement of emission from color center, silicon vacancy color center embedded in silicon carbide resonator, a larger than 100-fold enhancement on resonance with the cavity. Of course, we have also shown that all of that has been done for a single emitter based on second order correlation measurements. And in this case, the measurements were done on this V1 color center because of the orientation of the dipole relative to the cavity, but we're at the moment working primarily with V2 color centers. So where are we going from here? Well, I said at the very beginning that we're interested in building chip scale quantum networks, quantum simulators. The next steps would include putting things together. I already mentioned that it's clear that we'll never have a perfect platform, ideal system in atomic physics or in superconducting platforms. People also have to deal with inhomogeneities and imperfections and build reconfigurable networks or use tweezers, optical tweezers to reconfigure atomic arrays. We'll have to do something like that. I already showed you some of the tuning methods that we have. We can achieve that level of reconfigurability by doing, for example, second layer of lithography, identifying for quantum network applications as an example, where the high quality quantum emitters are, and then wire them using a network of photonics that we implement on top. And we can do that in silicon nitride on top of silicon carbide as an example. We can also do directly quantum frequency conversion in silicon carbide. I think that's clear now from the experiments that I've shown. So you don't really need lithium niobate or any other nonlinear crystals. You can do frequency conversion directly on the same platform that hosts your quantum emitters. Because for quantum networks, you certainly want to generate the output photons that are at the telecommunication wavelength range so that you can transmit them over longer distances. So quantum frequency conversion from 800 or 900 nanometers to 1.5 micron could be done directly in silicon carbide. Other things that we're doing include optimization, and Floquet engineering in time domain. While we've done some experiments where we modulate individual emitters with a pair of electrodes, I'll show you some of the other ideas that we're looking into pursuing, where we can get rid of some or most of these electrodes and apply only one pair of electrodes on the ensemble and still observe some exciting collective effects. But technologically, doing what is shown here is certainly possible, and it's something that people are also doing in other platforms such as superconducting systems. So how do we plan to implement the platform for quantum simulators or quantum computers? For quantum simulators, certainly we have to enable interaction of multiple qubits on the same chip. And I've shown you just the qubit part and how you can couple them to photonic structure and how you can drive them with some signal in order to interface them to each other. There is another important piece here of engineering that you can do in photonics that you cannot really do easily on other platforms, and that's engineering of the photonic environment. And here I'm referring to beautiful proposals by Ignacio Cirac from several years ago and Alejandro González Tudela, where they've shown that you can control the range of interaction between atoms or other quantum emitters inside of the array and control the Hamiltonian that you're simulating simply by controlling their electromagnetic environment. And there have been an effort in implementing this primarily in the group of Jeff Kimball at Caltech, but doing this in atomic systems is pretty difficult because you have to work with an atomic array which is coupled to engineered nanostructure in its vicinity. And we believe that this is actually much easier to implement in solid state where our atoms are already naturally trapped in its own environment. And by engineering dispersion of the structure, we can engineer the Hamiltonian that we would be simulating. Again, here we'll be relying on inverse design that I described earlier. In inverse design, we have already shown that we have the ability to completely engineer dispersion as desired. I mean, here are some examples where you draw a target dispersion for a waveguide as a red line. Manually, you will never be able to do that no matter what you do to this photonic crystal waveguide, whose one single period is shown here. But if you rely on optimization, you can exactly hit that target dispersion. For example, this was a group index of 25 in a large wavelength range, which beats any existing structures that people have designed by brute forcing. And you can actually do even other more sophisticated dispersion engineering. We actually use it, for example, in the context of microresonator dispersion, where we do dispersion engineering for resonators, for frequency combs, and insert some optimized elements like the ones shown here that actually do dispersion compensation so that you achieve the desired spectrum at the output. So clearly, it's possible to do dispersion engineering, and combining this with the array of quantum emitters, you can enable implementation of different Hamiltonians and control the range of interaction of atoms in the array by controlling their environment. So this was simply engineering of the photonic environment that is useful for implementing quantum systems or quantum simulators. But we think that there are a lot of exciting opportunities beyond just engineering of the structure and classical properties of the structure. And here I'm referring this as the quantum inverse design. And the idea is really to start from what we would like to simulate or implement in a quantum system and engineer the system, optimize the system, both in space and time being driving in such a way that you achieve particular response at the output. So this is similar to what we're doing in photonic inverse design, but applied to not electromagnetic wave equation, but instead applied to Hamiltonian describing a quantum system. So here are some simple ideas that we've already analyzed theoretically in that context that show you that something like this could certainly possibly enable some breakthroughs in a variety of platforms. So here, one idea that we looked into theoretically was getting rid of these multiple electrodes that are driving individual emitters in a resonator, and instead applying only a single set of electrodes. We still have homogeneously broadened emitters, as you see in this red plot here, that are basically decoupled from cavity resonance. So when you look at transmission through the system, you just see separately cavity resonance in three atoms. But then we started from that and found the optimal drive that we could apply to that single set of electrodes sitting on the cavity. So it's not really separate drives, just single drive, single set of electrodes driving all three emitters together. And for the optimized drive, we recover basically collective coupling of these emitters to the cavity, and we see Rabi splitting. So very simple configuration, but optimizing driving could lead to collective interaction and entanglement of the atoms to the cavity. And the other idea that we've studied recently was, again, can we take inhomogeneously broadened system of emitters, like 10 silicon vacancies inside of the resonator? They all have discrepancy in wavelengths, but we would like to use them for quantum transductions from microwave to optical frequency region. And of course, inhomogeneous broadening would be detrimental because it reduces their coupling to cavity and cooperativity and subsequently also efficiency of your quantum transduction. But we started thinking whether by optimizing driving on that system, either optimal or microwave driving, we could basically increase the efficiency of transduction. And these theoretical results that we have indicate that indeed by optimized driving, you can significantly improve transduction efficiency that is shown here. by about an order of magnitude for very realistic parameters of the system. So that's where we're going from here, and both theoretically and experimentally. And with that, I'd like to conclude my talk and just say that the combination of a variety of optimization techniques with new platforms in silicon carbide and diamond, but maybe some others as well, of course, should lead in the future to very scalable and quantum systems for a variety of applications, not just for quantum networks where typically these systems are considered, or quantum sensors, but I also believe that we'll be able to scale them to interesting sizes of quantum simulators and quantum computers. And let me thank our funding and collaborators. And this is my research group some number of months ago when we could actually stand all together outside of the building. Thank you very much for your attention.
Thank you for the very nice talk, Jelena.
Thank you, Kej.
I see a question in the chat box from Elizabeth. How does the modulation of the it's from the first half of the talk. So how does the modulation of the emitter during excitation compare to modulation of the photon following emission in terms of getting the desired spectrum?
Yeah, I think it's an interesting practical question. Of course, you can try to do modulation on the photons at the output. You can be limited. I mean, if you're talking about chirping the spectrum of the photon, probably at the output by using some kind of modulators and so on. There are limitations on how fast you can do the process at the output and what kind of spectrum you can build at the output. So there are some technological advantages to doing what we're doing now, where we're still working in the regime of kind of gigahertz driving on the quantum emitter. The other advantage I see in what I was talking about at the end, which is relying on using this optimized driving on multiple emitters. I mean, this is really what we're primarily interested in, although I think that there are applications for a single emitter where you can kind of control the output spectrum of the photon and use it to couple it better to a cavity or not. I think kind of the true strength of this approach is on taking any homogeneous set of emitters inside of a resonator or a structure and optimize the drive, kind of global drive on all of them in order to recover collective coupling, right, to optical structure. And that's what I was showing theoretically at the very end, but we're also working on this experimentally because although you can kind of bring a separate set of electrodes for each emitter and kind of tweak them on resonance, I think that approach is very difficult to scale in any platform that people are using. So finding how to optimally drive them in order to recover collective effects and entanglement is what I feel is the most exciting part.
So there is another question. There are 3 more questions.
Sure.
So the next one is from Semyon Bogdanov. Thanks for an excellent talk. Could you please comment on the integration of classical active components on the silicon carbide on insulator platform, like pump, detectors, etc.?
People use silicon carbide for electronics, power electronics, right? So as opposed to any other, I mean, there is also a lot of effort on wide bandgap electronics in diamond, but it's not as mature. There are issues with making electronics in diamond as opposed to silicon carbide, which is kind of pretty mature for power electronics applications. People use it for electric cars and also for variety of sensors, you know, also in the space program and satellites. So I think electronics is very mature. The issues of doping and are kind of mostly resolved. I know that some companies are working also on silicon carbide on insulator as well, although using smart cut techniques, which is what people use for silicon on insulator. So that would be of sufficient quality to do electronics, but probably not of sufficient quality for quantum optics that we're doing here because of this ion bombardment. But I know that they're also developing, you know, electronics in those thin film materials. So I think, you know, that's where the field stands. Not everything has been I'm not really familiar with the state of the art for silicon carbide detector, but so considering that, I mean, you can do certainly frequency conversion, and it's a wide bandgap semiconductor. You can in principle implement detectors, but the other option is it's fully silicon compatible. So you can also think of doing detectors in silicon or germanium, which you can also put on top of silicon carbide. So electronics works really well. Quantum optics works. Nonlinear optics works. So there are still developments that need to be made, but on the other hand, there is no other material that has all of these pieces already in the current stage.
Next is from Tadia Sled. For the specific problem of on-chip OFC, I assume it's frequency combs, what are the key advantages of silicon carbide versus silicon nitride?
What are the key advantages of silicon carbide relative to silicon nitride? I mean, silicon nitride is a pretty good material in terms of losses. I mean, but it is also quite limited in terms of the applications, right? So the loss that we have right now in silicon carbide is comparable to foundry-based silicon nitride. It's 0.08 dBs per centimeter, although it's probably going to be lower than that. I think you can certainly do frequency combs in silicon nitride, and people have done beautiful work on that, and also nonlinear optics in silicon nitride. Also in other materials like tantalum, I think the advantage of silicon carbide is that as of now, we can clearly do all of that and plus more, right? Because you also have quantum optics, you have electronics. So I think what is winning here is that it has excellent performance in nonlinear optics comparable to leading materials, but at the same time, it also has these other properties that enable you integration with quantum emitters or electronics or so on. But in terms of the frequency comb, it is comparable to nitride or tantalum. Although it is possible that we will see lower thresholds going forward.
So from Floquet, he has two wrong, but he said, nice talk. So he has a question about the inverse design. Basically, is that due to fabrication, the design you don't fabricate it exactly the same as the design, right? So how do this kind of fabrication influence the performance, and can you optimize the design such that it is more robust to imperfections?
Yes, definitely. So that's the main thing of inverse design, what we call fabrication constrained inverse design, right? So you can certainly design easily things that are, performing great, but you cannot fabricate because some features are very small or so on. And that's what we were initially doing in inverse design, but then we spent a few years working on what we call fabrication constrained inverse design. So that what you do there is in the optimization process itself, you introduce constraints that are coming from your fabrication process. For example, for diamond, we know that minimum features that we can reliably fabricate are maybe 100 nanometers, right? And that constrains the designs that you can produce reliably, but you have to incorporate that constraint that you never want to have any bridge narrower than 100 nanometers or hole smaller than 100 nanometers or some curvature which is smaller than whatever particular number that you introduce. That's all incorporated into the design process for a particular material. And what that means is that the design the process kind of is more constrained, and it takes more time to optimize and get to a global optimum that satisfies, local optimum that satisfies it. But when you design something, it will never have any of the features that you cannot reliably fabricate, right? So there are minimum feature sizes, again, curvatures. We can introduce wall profile. We can introduce edge depth. For those of you who are doing fabrication, you know that there is edge like that, small features edge slower than large features and things like that. And that's what means, what fabrication constrained design means. So once you obtain design that doesn't have any of those features that are not possible to fabricate, when you make basically the structures, the yield essentially is 100% because you are, unless there is some catastrophic failure on the chip, because you're basically never having any of the features that you are not able to reliably produce. And that's why when I was showing transmission results for measured structures, this is without any post-tuning, right there, because we designed them not to have features that we cannot fabricate.
All right. So I think, Jelena, you have like half an hour. You can stay over, right, for more questions. So if the audience have more questions, you can stay over. Otherwise, thank you for the nice talk again.
Thank you. Thank you all.